Afternoon, everyone. How about another beautiful day on the lovely Statendam? Sailing the high seas with a wonderful crew, and I'm very thankful for that. And you might say that to them also. They do a terrific job. We're going to start a new series. We're kind of done with astronomy. Let me say this though: we had a cloudy evening last night. We're not able to see the Southern Cross, so we're going to try that again tonight, even though it's not in your program. But let me caution you, please, to be very careful. I'll be up in the crow's nest a few minutes before 9. Then we'll go up above the crow's nest. They'll turn the lights out for us, and we'll see what we can see. Be very careful. It'll be windy. We are going this way at 18 knots, and the wind is coming from the opposite direction at about 18 knots, meaning there's going to be a 40-mile-an-hour wind up on top of the crow's nest. So please, both hands on the stairs. Do the lee side. That's the one that's not trying to blow you overboard. And then go right to the very bow or front of the ship where that plastic is, and there's a rail, and that will try to help keep the wind down. We're going to start a new series, Reflections of Chief Engineer. I wore my special Space Shuttle tie. It may be ugly, but it is certainly appropriate for this lecture. And we're going to talk about the world's first reusable space plane. Notice I didn't say spacecraft. Apollo changed the world forever, and America was leading in space exploration clearly, and that led us to the Space Shuttle. Here's a picture of Apollo 8, Earthrise, from the Apollo 8 astronauts on Christmas of 1968 as they entered lunar orbit, and when they came around the other side, here comes Earthrise. Spectacular picture. The Saturn V, the first manned flight of the Saturn V vehicle was on Apollo 8, and then we also landed 5 times on the moon. Apollo 11, 12, 13 did not land. 14, 15, 16, and 17. 6 times we landed on the moon. And we dreamed of a reusable space plane to build a space station that would become a transportation node to Mars. For the big rockets before that, there were 3 stages to get into Earth orbit, and each stage, after it burned its fuel, would be emptied and dropped into the ocean, and we never reused them. And we hoped to be able to be more like an airliner, that you didn't throw your airplane away after one trip, and that led to the Space Shuttle. And President Nixon announced that we could build the Space Shuttle in 1972. Early in the design had many different concepts. Initially, we wanted to make the design fully reusable and not throw anything away, but that required different types of shapes. Here's some of them early in the 1970s. And initially, the baseline was the first stage would fly back to Cape Kennedy and land and be reused. And then the second stage, which would go into orbit, the orbiter would do what our current orbiter does. But because of significant budget constraints, we ended up having to compromise this. It was about 3 times more expensive, we felt, than what we ended up with. So we had solid rocket motors on the side, built in Utah, near Promontory Point, where the Transcontinental Railroad was joined in 1869, interestingly enough, in terms of transportation revolution history. The external tank built out of in Michoud Assembly Facility just east of New Orleans, and it holds all of the liquid oxygen at the front third and the liquid hydrogen, which is not as dense, on the bottom 2/3, and they feed through large pipes 17 inches in diameter. That's the equivalent of the main guns on the World War II battleship Yamato. The biggest guns on the U.S. were 16 inches, so we're flowing propellants. Oxidizer on one side, fuel on the other side, through pipes that are this big around. The turbopumps on the Space Shuttle main engine devour so much fuel that they would empty your 25,000-gallon Olympic swimming pool in 20 seconds. Probably going to take you a lot longer to fill it than the Space Shuttle main engines could take them apart. There were awesome technical challenges, and the way we dealt with that was we determined that each of the NASA centers involved in shuttle development had specific skills that were learned during the Mercury, Gemini, and Apollo programs, and we built on those skills and those expertise and those test facilities. At the Marshall Space Flight Center in Huntsville, Alabama, we did structures and materials testing and certification. They designed and built the Space Shuttle main engine. There's those acronyms again. The reusable solid rocket motor and slash the solid rocket booster, and those are the individual four sections that make up the big solid rocket booster. We discarded only the external tank which was also designed and because it went almost into orbit, and then we released it and it would fall into the Pacific Ocean at a specific point so that we were not hitting shipping lanes or any islands. The external tank, of course, is the structural backbone. It's like the spine of our body, so it's much more than just a propellant tank or a fuel tank. It has to react the incredibly high forces of the solid rocket motors. Each solid rocket motor develops 3 million pounds of thrust each, just under that. And so those forces where the solid rocket motors attach at the front of the external tank, right here, and at the rear of the external tank have to be carried and reacted. And then we have a 300,000 pound, 250,000 pound, about the size of a DC-9 orbiter that is attached at the front and 2 places in the rear. It also has 3 main engines that are thrusting, burning the fuel from the external tank. Each main engine can develop 1.5 million pounds of thrust. And that's about equivalent to 30 747 main engines. One engine is equivalent of 30 747 engines, and that's why it burns fuel at such prodigious and huge rates. Huge temperatures and pressures to accelerate a launch vehicle from sitting on the pad to 25 times the speed of sound to go into orbit, 17,500 miles per hour. Stennis Space Center, east of the New Orleans, did the main engine testing and certification on test stands where we tested turbopumps and main engines, and they're a lot more difficult to build reliably than anyone who draws a view graph. If someone brings you a view graph of a brand new rocket engine, smile politely and ask them where they're going to test it for 10,000 seconds to make sure that it really works. Kennedy Space Center had the launch and landing facilities, also the recovery of the solid rocket motors and the refurbishment of the Space Shuttle orbiter. Johnson Space Center did all of the mission operations, the planning, trajectory work, guidance, avionics, computers, was in charge of the orbiter's development. And also we were the integration lead. That was one of my primary jobs, was system integration of all of these different pieces, controlling the interfaces, controlling the structural loads, what are the external environments that these other pieces of the shuttle system have to live to, and that was in our office. Reusable thermal protection systems, space suits, and that kind of stuff was done at the Johnson Space Center. We had to do major testing. Here is one of the early development engines of the Space Shuttle main engine at Stennis. Liquid hydrogen. Remember the Hindenburg hydrogen, extremely flammable, even in its liquid form. And then you mix that with liquid oxygen inside from these two turbo pumps, and then pour them into a combustion chamber and let them burn, and the gases go out at extremely high temperatures and velocities. So you can imagine that these are very difficult and very flammable and dangerous propellants. It's a big deal to get them running properly, not have them mixed together, and to operate at temperatures that are way outside of anything that we normally see. Liquid hydrogen is 420 degrees below zero to turn it from a gas into a liquid. Liquid oxygen, minus 250 degrees to turn it into a liquid. So metals react differently at these extremely cold temperatures. Seals, anything that's rotating that has to expand and contract, is sitting out on the pad at 70 degrees Fahrenheit, and then we hit it with these cold temperatures, so you can imagine the type of stresses that the metals go through. The solid rocket motors we tested in Utah. The first one of these that I saw in the late 1970s, what I remember was this huge noise, tremendous flame, giant plume of exhaust products going up into the Utah desert, and once it lit up and made all that noise, about 15 jackrabbits from where we were sitting took off across the desert. And interestingly enough, I still remember the jackrabbits. 122 miles, these burn for 2 minutes, and then we separate them. Their fuel is burned off. They have separation motors that we fire the bolts, the motors fire, and they move them away from the rest of the space shuttle. You don't want an uncontrolled separation where one of these boosters could swing back and hit the rest of the structure. Very controlled, worked wonderfully. They parachute into the ocean from about 200,000 feet and about 120 miles downrange. We also had to learn the aerodynamics and control characteristics of a vehicle. Here's the Space Shuttle orbiter. When it re-enters the atmosphere, in order to slow it down, we initially do a burn in the opposite direction that we're going of only about 200 to 300 feet per second. Not a very big burn, but that's enough to change the orbit and bring it down where it now re-enters the atmosphere. Then we turn the orbiter around 40 degrees from horizontal like this, and we are doing what's called, we're using the drag of the air to continue to slow the shuttle down from Mach 25 until it gets to much lower Mach numbers. And from the time we re-enter over the Pacific Ocean until we get over the Kennedy Space Center and land is about 12 to 13 minutes. We cross the coast of California, and about 8 minutes later we'll land at the Kennedy Space Center. So you can imagine how long a flight that is if you're going from Los Angeles to Miami. What is that, 5-6 hours maybe? And we do that in about 8 minutes coming down. That's so the temperatures are extreme. So, but notice these shock waves, supersonic flight, very high velocity called hypersonic flight that we did not ever fly aerodynamic vehicles at. We flew re-entry vehicles, we flew capsules, but not a winged reusable spacecraft. So the other thing that happens when I do this, use drag to slow me down, is I generate extremely high temperatures. And that was the difficult problem of the reusable thermal protection system. On the leading edge of the wing, 2,500 degrees during this controlled reentry. That melts any metal that we have, and what we used was a special carbon fiber that could stand those kind of temperatures with an aluminum substructure to attach it to the leading edge. On the bottom, we used very pure silica, basically spun glass fibers. Think of the, when you go to the circus and you buy one of those cotton candies, you know how that cotton candy is very light. It's very thin. That's what these tiles are sort of like, about 3 inches thick at the bottom with a black coating, specially designed coating that would radiate the heat away. And then the spun glass, highly purified, its purpose was to provide a insulation so that that heat would not transfer from the outside of the tiles to the aluminum substructure. The aluminum substructure starts to weaken significantly if it gets above 500 degrees centigrade. And so we designed the substructure to not see temperatures higher than about 300 degrees. That I've talked about. Here's the thermal protection system, and every one of these tiles, because it has a different temperature profile, this is the temperature profile. Notice the leading edge is the hottest with purple. Yellow, red is hot on the outer parts of the wing and the tail part. So from this information, we could design tiles at the proper thickness to take this different heat layers or heat distribution. It's not the same over the whole thing. Every tile had a unique number. It only went in one place, and it only had one shape. So you can imagine, those of you who are working in the library on the jigsaw puzzle, this was one of the world's biggest jigsaw puzzles during the 1980s, 90s, and 2000. And we had to have a special way to hold them onto the structure, because the temperature causes things to expand and contract, including these tiles. If we had bonded the tiles directly to the aluminum, that heat expansion and contraction would cause those tiles to fracture. They're extremely delicate. If I put one right here on this table and I took a silver dollar from about this height and dropped it on it, it would fracture that tile. Therefore, we had what was called a strain isolation pad. It was like Nomex, which is the fire-resistant people that the race drivers use, and it would be bonded to the metal, but it had a structure that allowed that tile to flex a little bit and move back and forth and not transmit these forces that could break it from the understructure to the tile. Now, having said that, in between each of these tiles would be a gap, right? And they can't be exactly tight together, or they'll also break each other. So the one of the big problems was to build a special circular titanium gap filler that could squeeze and expand and keep that gap closed, covered by a high temperature resistant carbon material that would go in between each one of those. Very labor intensive to repair or replace this whole tile system, and that turned out to be one of the real jobs that took the most time to get the shuttle back flying again. Here's the leading edge, very complicated. These tiles along here, one of which was fractured on Columbia from the big piece of foam that hit the wing right about where my arrow is, knocked about a 6-inch hole in one of these panels, and those hot re-entry gases basically melted the wing off over a period of time from just west of California to over Texas. Major testing: we tested the external tank in the Tennessee River at Marshall Space Flight Center. We took the shuttle, put it inside here. It makes tremendous amount of noise, so we had the biggest sound woofers on the planet that would shake, rattle, and roll what we predicted would be the noise or acoustic energy from the shuttle's engines igniting, solid rocket boosters igniting prior to takeoff. And it's much, much more dramatic and shakes the structure than you would ever believe. Main engine testing at Stennis, we turned a lot of the Mississippi water into steam by testing each one of these engines. Then we wanted to check the control characteristics, the gliding, approach, and landing systems. And so we carried the Enterprise, which was not designed to go into space, but was the test vehicle for what we called ALT, approach and landing tests. And we did that in 1977. Shuttle is on top of the 747. and the 747 starts a descent. Shuttle is a positive angle of attack and basically drops the 747 as it lifts and flies away. First two flights with a tail cone, we were concerned that we didn't understand the aerodynamics of the main engines out in the open, so we smoothed it up. And we learned from the first two drop tests that we needed to tweak the control laws so that when we did not have this cone on the back, which we did not have when we launched it, that we would understand the landing and aerodynamics of the shuttle coming in without this cone. And we did the last test without it and verified the corrections we had made were correct. We stacked it in the vertical assembly building or vehicle assembly building. You start with a booster, add a section, 2, 3, 4, put the top piece on, go to the other side, put the bottom one on, 2, 3, 4, top piece. Right here has to be within 1/4 of an inch from the time that you started back here, and now you're 280 feet up in the air. So we had to align these very precisely, because what we did was stack both boosters, then brought the external tank in, put it down between them, and we learned using special lasers and stuff how to stack them so that they were that accurate, so that when we put that external tank in there, it fit exactly right. Then you bring the orbiter over on its landing gear, pick it up with a big structure, fold the landing gear up, lift it in the vertical position, take it up 25 stories over the top and slide it down against this stack and put it together. Then you roll it out on the world's biggest tracked vehicle, mobile launch platform, to the pad. And in fact, this is the mobile launch platform, and it acts as the launch pad. Not only does it transport it out there, but it stays there, and then we launch the shuttle from there. Prior to the first flight, we had to verify all of the ground computer systems, command, control, propellant, loading, stabilization, pressurization, huge programs. And so we would take the vehicle, fill it full of propellant, and then we would light only the main engines. The reason the shuttle didn't lift off, and we calculated this, it wasn't exactly an accident, is that the whole vehicle, fully fueled, weighs 4.5 million pounds sitting on the pad. The three main engines only develop 1.5 million pounds of thrust, so it's not going to lift up unless you light these solid rocket boosters, and we told them not to light. And what we did was we verified all of the propellant systems, that we could start these engines safely, we could shut them down safely, because once you lit these solid rocket boosters, it was going somewhere. And you would really prefer that you had control of where it was going and that you had properly released the bolts, etc. We did that in February of 1981. And then we launched on April the 12th, 1981, interestingly enough, exact the 20-year anniversary of Yuri Gagarin's first human orbital spaceflight. Was in April the 12th, 1961. Our Russian friends still celebrate Gagarin Day to this day. They just had that last month, and they have a big party for their great achievement to put someone in space. I was a guidance specialist, worked for the guidance that went inside the Space Shuttle's computer, monitoring as it went up. Is it going on the right path? Are we going into the correct orbit? That was the first mission that I worked in the Mission Control Center. I worked the first 16 of them. My dear friend and one of my mentors, Jim Ianson, was a World War II B-17 pilot in the Pacific. Great guy. And when we got out of the elevator after we were successfully in orbit, this old helicopter pilot here, for his first rocket launch, was about 6 feet off the floor, hovering. And he said, "What did you think, Frank?" And I said, "It worked. That damn thing worked," which I was pretty amazed. And here's our first crew: John Young, Robert Crippen. John Young was the only astronaut to fly 3 different spacecraft. He flew with Gus Grissom on the first Gemini spacecraft. He flew on 2 Apollo missions, one of which he commanded. and he was commander and head of the astronaut office for the first space shuttle flight. Robert Crippen was his co-pilot. Some keys to success. Notice that this was entitled Reflections of the Chief Engineer, and engineers always have this thing of, well, what did I learn? You know, what were some of the principles that helped us be successful? I also give this lecture to new NASA engineers, and so I find it useful to step back, reflect on what is it that you did right, not just focus on what you did wrong, and you will do some of those. But we had a clear objective, a common goal, and we built on the past success of hardware facilities and hard-won experience. I call that standing on the shoulders of giants. Von Braun, John Glenn, you know, there's a list of tens of thousands of people who made America a leader in space. So we took their experience and what they did and their hardware, and we stood on the shoulders of giants. We divided the labor that was aligned with the key expertise and facilities of the different NASA centers. I talked about that earlier. We had engineering excellence, outstanding people. We built on the past processes and successes, facilities, tools, and a budget to do the job. We wish we'd have had more budget. Well, welcome to the real world. You don't get to have everything that you want. We built on multi-center contractor relationships. We basically had a badge-free environment. It didn't matter if you worked for Boeing or you worked for North American, Rockwell, or Downey, or Pratt & Whitney, or United Technologies. We all had this common goal, and we didn't worry about what color badge you were, either contractor or civil servants. And this is difficult for humans, because our human nature tends to dominate our actions. Acceptance of a better idea from somebody else's center is really a strength. It's not a weakness. Think about that one in anything that you do. Our first thing is, well, it's not invented here, so I'm just kind of, maybe I will ignore that. Or these centers that are in Alabama and Florida and Johnson Space Center, we tend to become stovepipes. We talk to the people around us, and you have to really reach out and remember. I know somebody at the Kennedy Space Center who has that expertise, or up at Cleveland, at the John Glenn Space Center that has that expertise. So you have to build a working relationship. Trust is key. One of the things I learned was lead from the front and by example. You can use that one in your own home with you and your children and your grandchildren. Communicate, communicate, communicate. Here's one of my screensavers. During a part of the 1990s, we had 2 shuttles on the pad. We had 2 launch pads, Launch Complex 39A and B, that were used for the moon missions. We also developed a Buck Rogers spacesuit that we could put on, and we had cold nitrogen gas, a little control device here so that the astronaut could fly it. And Bruce McCandless flies like Buck Rogers in 1983 on the 31st shuttle flight, called the MMU, Man Maneuvering Unit, built by in Denver by Lockheed. And Bruce leaves the cargo bay and flies alone in space. What a picture that is. Here's the Earth in the background, and Bruce is out there looking back at the space shuttle. Terrific picture. Another unique and amazing capability of the space shuttle is it could repair and service satellites. George Pinky Nelson goes out with a specially designed device on his belt to go out and grab this satellite, which had malfunctioned, was not operating properly, was in low Earth orbit doing zero science, which is, you know, you spend a lot of money to send a satellite up there, do science. We brought it back in the cargo bay. We already knew what was wrong, took the spare parts up, and the first time that any satellite was ever repaired in orbit, fixed, then released it, and it went on to complete its mission. There's the Solar Max with the Canadarm. After we grabbed it, put it in here in the cargo bay, our garage, and worked on it. We had several satellites, communication satellites, that NASA didn't design. There were 2 in a row in 1984, Westar and Palapa. They have the shuttle would carry them up into low Earth orbit, 220 miles up, release them. They had their own rocket motor that would take them to 22,500 miles. That's where all of the communication satellites live, in what's called geosynchronous orbit. Arthur Clarke, a science fiction writer, wrote about this in the early 1950s. And the reason that orbit is so valuable, when I'm 200 miles up, I orbit the Earth once every 90 minutes. When I'm 22,500 miles away, I orbit the Earth once every 24 hours. Okay, did you hear that? Once every 24 hours. So this orbit is so valuable because as this satellite is going around the Earth, it's going at the same speed as the Earth is turning. So I can fix an antenna on my roof. Most of you have them. You're looking at television stations and all that. And I don't require any complicated mechanisms to track this satellite. That's why it's so valuable. They put it up there. They point it in the right direction at that satellite. They verify they've got the maximum signal strength. And how many of you have been up on the roof that you had to repoint your antenna? You did. I hate it when that happens. I've been fortunate and not have to do that. But it's a very valuable piece of real estate because it allows us easy communications without having complicated pointing mechanisms. I went down a rabbit hole and digressed. These two satellites in this time frame, they had made a generic design change, not a NASA motor. It was somebody else. I don't even remember who it was, Aerojet General or somebody. And they had a design flaw. Both of these satellites we released on the same mission. The engine, they commanded it to start, it went. That's not how you get from 200 nautical miles to 22,000. Both satellites were stranded in orbit. These satellites cost, maybe $1.5 billion. So what we did was we went worked with Westar and Palapa and says, maybe we can go up here and figure out how to grab these, put them in the cargo bay, take with us a new motor that you have proven works properly, right? That won't go, that will really go. And we took the new motors up. Dale Gardner and Joe Allen went out, captured them with their manned maneuvering unit, Space Pack, captured them, brought them back in. We put new motors on. Here they are in their sign. If I could blow that up, that says, it said something like da-da-da's repair and salvage. Gardner and Allen salvage or something for sale. And we repaired them, and then the shuttle came home and they went to successful orbits. Similar thing, different problem. STS-49 was also stranded in low Earth orbit, and Intelsat 6, very large satellites. We went out with this special bar that we hoped would capture it, but every time Pierre Thiot went out and tried to grab it, it kept pushing it away. We finally put 3 astronauts out here, and Dan Brandenstein, Navy carrier pilot, Vietnam era, did some of the best formation flying. They went 1, 2, 3, and the 3 astronauts grabbed it up here with their gloved hands, and then somebody stuck that tool on that wasn't working, and we've got it in the cargo bay and we fixed it. So the other reason for a mission control and a ground team is don't be surprised when things don't go the way you planned. So we installed the capture bar, and then after we put the new perigee motor, the new rocket motor, we deployed it again, and it successfully went on into 22,500 up geosynchronous orbit and functioned properly. NASA also launched the great observatories. We talked about some of these in the astronomy section. Hubble Space Telescope sees invisible light. Spitzer Space Telescope sees in infrared. The Chandra X-ray Observatory sees X-ray, and the Compton Gamma Ray Observatory sees the very highest energy electromagnetic waves called gamma rays. We repaired Hubble. Once we took it up, remember we had a flawed mirror, we fixed it, here's the astronauts fixing it, and then we kept upgrading it over the next 15 years to have better and better instruments, new solar arrays that didn't flex when we went from light to dark, which we didn't anticipate. We flew, we learned, we paid a terrible price. But we fixed it and we kept flying. And this was the first launch that I saw from the Kennedy Space Center. We had a burn through of the solid rocket motor. What happens is when you put those sections together, you have a circular tang, and above it a clevis that grabs it on both sides with two O-rings out here where my fingers are. What we didn't understand was at very cold temperatures, when you light this solid rocket motor, it rings like a bell. So this joint was flexing. And at warm temperatures, those O-rings would track that flex and not allow the hot gases out. At this very cold temperature, it actually froze overnight in Florida on January 27th. We had long meetings. Should we go do this launch? Everybody was involved. We said, we don't know of anything that this cold weather would hurt us, but we didn't understand that at very cold weather, those rubber O-rings are now stiff, and they will not track that gap. The hot gases burn through about 70 seconds. There's the plume. It burned the right rear attachment point off. It pivoted and caused the external tank to explode. There's our brave Challenger crew. STS-107, Columbia. This is very difficult stuff. If you had bare metal up here, and up at the top of this thing you have minus 250 degrees centigrade, and at the bottom minus 420 degrees centigrade without insulation, what you do is you freeze the air, and you would have about 4 or 5 inches of liquid ice, liquid nitrogen dripping down all over the place. So you must insulate it, because all of that stuff can fall off and damage the thermal protection system. Notice the very complex geometries. These ramps, this is where the front of the orbiter is held onto the tank, and this is a strong structural ring, very complicated geometry. This is called an aerodynamic ramp, because as we're accelerating through the atmosphere 4 times the speed of sound, we're generating tremendous pressure and shock wave, and without this shaped ramp, it would just blow that insulation off and perhaps burn and damage this attachment point. But the problem was we had to spray that on by hand and then get it shaped with a sharp knife, etc. And then when you put these very cold propellants in here, the tank would physically shrink about a ½ inch in diameter. That put stresses and pulled this insulation away in certain complex places. Then we would liquefy the air behind it, and then once we lift it off, in about a minute and a half after we fly, we're going past the speed of sound, we're generating heat, that air expands, and it blew off a big piece of this insulation right here, which hit the wing, made a hole like this. This is the ground test that we did in San Antonio with this piece of foam about the size of a small suitcase, a small briefcase, caused that damage when it hit the wing at 500 miles an hour. You say, now, well, how could it go 500 miles an hour from here to there? The reason is this foam is very, very light. Think of you're driving down the street in your car, you throw this piece of foam out, the wind hits it, and it just slows down immediately, right? And here's the orbiter, which has got 6 million pounds of thrust behind it, accelerating toward it, and the relative velocity when that piece of foam hit the wing was 500 miles an hour, and it made that hole. And there's our wonderful Columbia crew. We had convened a Columbian Accident Investigation Board. I actually had come back from Washington, D.C., retired the night before Columbia went down. Got a call, said, turn your TV on. Here's pictures of Columbia breaking up. So I didn't go in Monday morning and sign the retirement papers. Being a good ex-military, I reported for duty. And they assigned me to work with Admiral Hal Gaiman, 4-star admiral, was in charge of the Atlantic Fleet at one time in his career. He also led the USS Cole bombing investigation. Sally Ride, who's no longer with us, our first woman in space. This was one of our meetings during that Colombian accident investigation. My job was to put together a team that would do everything that this 23-member board needed. We'd record the results. We would record what they asked for. We would archive all of that. We would do the analysis, give it to them, and I was the leader of that team. Flight experience led to success. This is a complicated machine, the most complicated machine ever made by man. Here's some of examples. I won't go over them in a whole lot more. We fixed that SRB joint. We fixed those foam failures. We had some computer problems from the zero gravity that never showed up on the ground, caused 2 of them to fail. Auxiliary power units. We improved the turbo pumps of the main engine, and etc. But one of the things that I teach my NASA new students is flying with design deficiencies that you think you understand completely requires extreme caution. I'll give you an example. In the turbo pumps of the main engines, we found that they started getting cracks, tiny surface cracks in their blades, not deep cracks, but surface cracks from this terrible temperature change as they went to their full operation. We did not design those turbine blades to have cracks in them. The turbine blades of the fuel pump are turning at 70,000 RPM. 70,000. Your engine on your car, you're revving it if you get 5,000 out of it. So a little crack in a blade, if that comes apart in either an airplane engine or especially these rocket pumps, it's catastrophic. So we flew them for a little while, and we kept telling ourselves that those cracks won't propagate. And you just have to be really cautious with that, because computer simulations are not always represent the real world. The other thing I learned is that better is the enemy of good enough. So now I've told you that we had on a previous chart a lot of improvements that we needed to make, but the trick of the chief engineer is to say all of our engineers want to tweak their designs. They get bored. So they want to say, let's do this, let's do that. There are unintended consequences of making design changes to equipment that's operating in these extremes, and you have to have a lot of experience and judgment to say, no, that is not a threat. That's not going to kill our people, and that's not worth tweaking. It's good enough. Truthfully, the Russians were better at this than Americans. We love our new technology. But I challenged our folks to do quantitative risk. Are you really working on the thing that has the highest probability of killing you? And are you really making a change that needs to be changed? Better is the enemy of good enough. Then we went on to work with the Russians in 1994. It was absolutely the right thing to do. We built this hardware that let us dock with the Mir space station. I initially thought this wasn't worth doing, but it turned out I was wrong and the NASA administrator was correct. It was extremely valuable over this 4 years, 10 times, to build that trust relationship with the Russian space engineering team. If we'd have gone directly to the International Space Station without doing this, I believe we would have failed miserably. So remember that one as a reflection of a chief engineer. You must have trust, and that takes time and experience to build. And now, if we have the national will and the leadership, I hope we go on to Mars and we continue exploring our solar system. This is a great picture. It occurred in 1992, the 500th anniversary of Columbus finding the New World. He may not have been the first, by the way. There's some interesting new books that suggest, called 1421, that China may have discovered America, especially the West Coast and all of South America, long before we Europeans did. But here's the Nina, Pinta, and Santa Maria. Here's the shuttle in the background. Love that picture. I've done better with my time today. I was reminded that I only have 45 minutes and I've used them up, but I'm going to come right back over here, and that gives them time to set up. And really, it's rude for me to go as long as I did yesterday, and I apologize to the folks that came back after me and the team that works our sound and all that. Give them time to change. But after I close all this stuff up. I'll be right back there in the corner and be happy to answer any questions for you. Tomorrow we're going to talk about the International Space Station, which I had the honor and privilege of being the chief engineer for after doing that for the Space Shuttle. So thank you very much.